organizador de este 10º Congreso Nacional y Tercer Congreso Internacional de Riego, Drenaje y Biosistemas, para que presente a nuestro primer conferencista magistral. Doctor Waldo Ojeda, ¿cómo estás? Muy buenos días. Adelante, por favor.
Okay, now we are going to change in English since Mr. Ravindra Ulangwar, he's in India, no? He's our first keynote speaker. This is very important person in India, and we are happy to have Mr. Ravindra here. I'm going to introduce him, his resume. He's mechanical engineering and also he has a MBA in marketing management from the Symbiotic Institute of Management in India. And something very interesting, also he was a Fulbright scholar in 2009. The Fulbright in the United States is very famous for most people attending in the United States to get a master or high-level studies. It's very important for us because he's involved in for many years, like in his professional career, related with the design, planning, and construction of various and several projects from drinking water and utility water, and especially for irrigation system in water supply, not only for agriculture, but for industries in India and in the international market. This is the top 25 certified international professional engineer. We call it the PE, Practical Engineering in India. Is fellow from the Institute of Engineering in India. Is vice president from the Head and Water Management and global lead for irrigation business for Willow Matter and plant pumps. He's also instrumental in the design and building of one of the world's largest pumping system projects in Surashatra Branch Canal pumping station for the Sardar Sarovar Narmada Naiwan Ltd in Gujarat, India. It's important because this project provides drinking water for 30 million people and irrigate about 500,000 hectares. The success of this project has transformed the economy of this state, or the state of Gujarat, by watershed management. So it's a pleasure, Professor Ravindra Ulangwar, to have here. And now we are going to have your presentation in the screen. We are connected now. Please, can you put all the presentation?
Yeah, right. Yeah, I'm sharing. Yeah. Okay.
So we can now to start this.
Can you see the presentation?
We have aquí tenemos la presentación, ¿no? Okay. I think you had the presentation over there. Can you share?
Yeah.
Okay. The name of the talk is the design, planning, and construction of irrigation system projects in India. Please, okay. Vijay, I don't know if you have the presentation. Can you share it over there? We're waiting for, okay, go, okay. Yeah, we are seeing. Can you put it in the presentation mode?
Yeah.
Yeah, we are now we are watching the presentation. Okay, good. Good. Ready?
Yeah.
So we are ready.
Yeah.
Ready.
You are able to hear me and also can see the presentation?
We see you. We see you and hear you very well. Go ahead.
Can you hear me clearly?
Yes, we hear you very well.
Yeah. So first of all, thank you very much. Very good morning and warm welcome to all the participants, organizer for the 3rd International Irrigation and Drainage Meeting, organized by COMEII 2025 and IMTA. So my topic today is design, planning and construction of irrigation project in India. I am really honor and it's my privilege to be here for such an august gathering. And I'm really thankful to Mr. Waldo Ojedo, President of COMEII, Dr. Alberto Gonzalez, the coordinator for IMTA, and also my friend and well-wisher Dr. Vijay Lapshetwar from ICID India, who introduced me to this August gathering. So I'll be taking you through my own experience of designing, planning, and construction of a smart irrigation project in India. Okay, Buenos dies a todos, as an honor, Mr. Equicon Sted Hoy. I just try to speak to you in Mexican language. So wishing you all very good morning. It's my great honor to be here. Okay, just to give you idea to connect, like in the opening session, it was mentioned that by Mexico and India has a lot of similarity. Just to give you idea, how is the Indian account for 18% of a global population. You know, we are one of the largest populated country, almost 1.4 billion people, 1.4 billion plus, but we have only 4% of water resources, world's water resources. So that you can understand what is the stress on the water resources in India. The highest people, but only 4% of water share of the world resources. The average rainfall in India is about 4,000 billion cubic meter, which is very large. But the issue is we have a lot of water, but the water is available where it is actually more at where it is not needed. So the issue is we need to take the water from one place to other place where it is really needed. So most of the country's rainfall over a 4 months period, June to September, and I just was going through the Mexico's also geography, and I came to know most of the time Mexico also has same period, 3 to 4 months of rainfall. So more or less India and Mexico challenges are same, and this rainfall is very spatial, and also throughout the country we have very uneven distribution of rainfall. I think it is a similar situation in Mexico also. Just to give you idea, India river basin. So here when we talk about irrigation or agriculture, we talk about the river basin and hydrological zone, which normally the water resources are talked about. So these are the various river basin. You can see the map of India. So this just to give you the perspective of how the water are actually, which are the major river basin and how the water resources are distributed throughout the country. So the catchment area is 20,000 square kilometer, and there are 12 river basins, 12 major river basins with the total catchment area of 2.53 million kilometers square. So out of which you can see the yellow part, you can see this, I don't know, can you see my mouse there? So yes. This yellow part is one of the largest river, you know, I think many of you must be knowing. We have one of the largest and holiest river in the country is called the Ganga. And this is the Ganga, Brahmaputra, Meghna. This is the largest basin with a catchment area of 1.1 million square kilometer, which is more than 43% of total catchment area in the country. So there are many other rivers which has the catchment area more than 100,000 square kilometer, like Indus, Mahanadi, Godavari, Krishna. So if you see the northern part of the country, which has a lot of water, but not the same case in other part. The western part actually is very less water because there are hardly any rivers flowing in the western part, this part. You can see the westernmost, which is the Gujarat, which was mentioned in my also introduction. We did a one big project in Gujarat because there is no water. So the big dam which was constructed on one of the river called Narmada, and there is a big canal network to feed the water to this for irrigation and drinking to this zone, western zone of India. So just to give you idea about the India, so you know the perspective how we are talking. The 46 medium river basin with a catchment area between 2,000 to 20,000 square kilometer. Okay, just we saw the major source in irrigation in India is actually the surface water, which is the river basin. Just now we talked. So if you see the major irrigation surface water, which is in a blue area. So here we have one of the largest rivers flowing in the country. So you can see many blue patches, which is based on the surface water. And then we have minor irrigation, which is shown into the red colors, which is actually basically the groundwater and small reservoirs and the tanks. And the yellow patch, what you can see is the rain-fed crop, rain-fed agriculture. So other area like a forest and natural. So this blue, red and yellow, these are the area of interest. You can see it is very unevenly distributed. And there are a lot of water bodies all across the country. Okay, but at the same time, there are a lot of emerging opportunities in India based on the recent trend. So Indian irrigation system market is poised for remarkable growth because we have 1.4 billion people to feed. At the same time, the Indian economy is totally based on agriculture. We are agro economy, mainly similar to the Mexico. The projected, the CAGR, the compounded annual growth rate is close to 11% during the period, the same period when we are talking 2023 to year 2028. And India is one of the second largest arable land area encompassing 141 million hectares. And out of which the irrigated crop area is almost 50%, which is 71 million hectares. And there are many government. Actually, in India, the irrigation sector is governed by many government policies from the federal government as well as from the state government. And there are many programs which are driving this irrigation sector, which is all the funds, finance is from the government. So all the big programs which are now currently implemented in India are backed by the government funding. So there is one program, we call it a Prime Minister program, is actually US $7.7 billion in one of the flagship program of the present government. So there is a huge push from the government to develop the irrigation infrastructure in the country. So if you see how the irrigation, in fact, in India is, we are dividing the irrigation projects in a small irrigation. Actually, any project which is less than 500 hectare is called a small irrigation. The medium irrigation projects are between 500 hectare to 2,000 hectare. And the major irrigation are actually close to 10,000 hectare. So any project which is more than 10,000 hectare is called a major irrigation project. So most of the projects which are actually classified as a small, medium or major based on the command area, that is which is defined in a hectare. So recently in country, we have a trend and there is also government policy, which actually we call it a pressurized distribution network. So I think during opening session, we mentioned that in Mexico also, there are a lot of canal-based projects. Similarly, now the pressurized distribution network where the water is taken from resource to the root of the crop or to the boundary of the farmland through the network of a pipeline. So this is a pressurized water because there is a pumping system, and through pumping we develop a pressure so that enough pressure is available at the farm boundary, and this is also called ready for micro irrigation. So now what is happening, you saw the country which has very, very uneven water distribution. So there are many areas which has a surplus water and some areas which has deficit water. So government is also putting up a large infrastructure project where they want to transfer the surplus water from one river basin to the river basin which has a less water, so that they can protect this area from the flood. The river basin with a high water resources are prone to the flood. So they can, when they transfer the excess water from one river basin to the other river basin, they protect the area from the flood. At the same time, they make the water available in the other basin where there is a scarcity of water. So the government of India are now launching a many project where they are linking the river basin for transferring excess water from one basin to other basin. And the primary objective of this project are for creating the irrigation resource. So we just mentioned we have two source groundwater base. So normally these are the open well and also the bore well. I think it is a similar situation in Mexico also, because groundwater is, I think there is a lot of exploitation and the water level is very speedily decreasing, and we have more higher capacity pump to draw the water from the long this borewell from the depth of the earth. We have surface water based, mainly all the big projects, which we call it a community irrigation projects, are based on a surface water. And the source of this water is either the lakes or the dams and the canals and the river. So India during last 75 years have built many dams, and almost I would say all the potential where we can build a dam has been harnessed by government, by the central, federal government. Mainly this is the state government subject. So all the states, they have developed the dams, and these dams are the primary source of irrigation and also for the drinking water for the communities in the rural part of the country. And also this dam has their own canal network. At the same time, many rivers, which has a perennial rivers, we have many large rivers, which we saw in the beginning in the river basin. These are the perennial rivers which flows all the 12 months, are also the source of irrigation, because the many projects, large size projects, are built on a river. And one of the case study which I am going to present is also the river-based, large community-based project. In surface water, there are two types. Initially, when India was independent, so initially we started with a gravity irrigation. And once the gravity irrigation, all the command area has been covered, then second phase came with the lift irrigation, where you can see in the picture top, in a large river, they have built a pump house, and there are battery of pumps, number of pumps are installed. These pumps are lifting water from a river, and you can see this rising main, the pipeline, and they're lifting water and taking it to the higher elevation where there is a command area, which normally cannot fed by the gravity. So you need to lift the water from one level to the other level. And then there is a series of pumping. Sometimes it is a one stage, sometimes it is two stage. So we have, this project is also, I was involved. This is one of the big project in the central part of India, the river called Krishna. And one of the largest pump house, when it was constructed 20 years back, one of the largest pump house in Asia, I would say. Okay. So we have either single stage pumping or we have multi-stage pumping. We call it a series pumping. If the command area is very, very high elevation, then we also take one pumping station, take water to the pumping station 2 and then 3 and 4. Likewise, depending on how the command area is distributed at a different level, the water is transferred from one place to other place with the help of pumps in the large pumping station. So last, I would say 10 years, the country is shifting to the system called a pressurized distribution network, along with the SCADA system. SCADA system, all of you are aware. These are the programmable logic controller and also the automation. We call it a SCADA system. So in pressurized distribution network, there are also two types. One is we are lifting water and taking water to the delivery chamber. And from delivery chamber, the water goes to the pipeline network through gravity, and it goes up to the farmland. So it is two-stage pumping, first pumping and taking it to the various delivery chambers, which are located throughout the command area, depending on the topography. The highest point, normally we put the delivery chamber so that all the area below delivery chamber can get enough pressure at the farm boundary. Second system in a pressurized system is direct pumping, in which there is no delivery chamber. The water is taken directly from pumping station through the pipeline network up to the farmland. Up to the 1 hectare is the outlet in a farm boundary, where the farmer can connect either sprinkler irrigation or drip irrigation. These are the two popular micro irrigation systems in India. I believe same with Mexico. Now we don't have a central pivot system yet because the unit farm size in India are normally very small. Farmers farm holding size is hardly 2 hectare or 3 hectare. So it is not feasible to put central pivot system in India. But there is a lot of government program, there are a lot of financial programs or financial support given by the government for a farmer to go for either sprinkler system or a drip system. Depends on which is the crop and how is the soil. So, but these are the two most popular micro irrigation system in India. Just to give you idea how big is the Indian market. So we have 141 million hectare of a net cultivatable area, out of which the irrigated area is 71 million hectare. So in fact, I think it is Mexico has 6.5 million hectare, what I know, the irrigated land. So we are 10 times bigger than the Mexico as far as net irrigated area is concerned. And again, it is distributed by groundwater. So almost 43 million hectare is groundwater, and only 28% is covered under micro irrigation. So out of 43 million hectare, 12 million hectare is covered under micro irrigation, and surface water 28 million hectare. And the micro irrigation coverage is very minimal. Actually, it is negligible. Because this big area, groundwater based schemes are all government finance, whereas surface water now just starting in a big way. So slowly farmers, once the water is available at a farm boundary, the farmer will adopt sprinkler or drip irrigation. So we have the program which is called per drop more crop. That is the motto or tagline of the government program, where they want to harness every drop to generate or to grow more crop. So it is called more per drop more crop. Okay, now just I mentioned, India is shifting from a canal-based system to the pipe-based system, which according to me is a big revolution in improving the water efficiency, which all of you as irrigation engineers also agree. Because here there's no wastage of water, and the biggest problem in India is if you have to put the canal, we have to acquire the land from the farmer, which is on a permanent basis, and which is a big painful process, and it takes long time to get the land from the farmer if you have to lay the canal. And this is the one of the reason many irrigation schemes were not so much effective, because they could not develop the complete canal network in covering the whole command area. There was some gaps, and then the water could not reach to the tail end. So the farmers at the tail end were suffering. And so that is why now, as per government policy, We have to, any project in irrigation project in India by government policy has to be through pipe network. We cannot, new project cannot be with a canal. You know, there are many advantages through pipe, no wastage of water, no theft, no evaporation, and there is an equitable distribution because every farmer up to tail end can get the water, better control and management, no contamination. You can open the, as per the irrigation calendar. There's no maintenance. Canal has a huge maintenance and silting and all this, you know, and the projects are happening very fast. Now it has come down almost 40% time. Earlier, we used to take, say, 5 years. Now they take 2 years. And since there is a increased water use efficiency, in the same water, 50% more land can be irrigated. So this is now government policy in India. All projects should be with pipe irrigation. Okay, I think I'll run a little bit fast. Smart. So we call it, when it is a pipe irrigation, it is a smart irrigation because those are with a pumping and a SCADA system. So we know that the benefit of smart irrigation, you all are experts, so you know. But just to touch upon, basically, it is helping farmer to generate more income from more because of higher water use efficiency and agriculture productivity. The yield of the crop has gone up very substantially, which is generating substantial employment in a rural area. Earlier, many people from the rural area, they used to take one crop during the rainy season, and later on they used to migrate to the big cities for earning the money because there is no water after the rain, so they don't have any work. So they go to city, and then you go, you know, the city is crowded, lot of urbanization and all associated problem. So because now this water is available in the farm for second season and the third season, the reverse migration, we call it a reverse migration. Now, these people from a rural area are not going to cities and they are busy with their own farm. So which is bringing a lot of social benefit, bringing happiness, the community, the family life is gone up. A lot of social issues are resolved. And the other benefit like recharging of the water and global warming. So I'll take you through the success story of one of the state. We call it a Madhya Pradesh. This is an India map you can see. And this state is right in the center in the India. And that is how the Madhya is the center. Madhya is an Indian Hindi name, which Madhya means a center. Pradesh means a region. This is a central region. So this state has a done remarkable work in the development of advanced smart irrigation system using this pipe distribution network where the water from the river or reservoir through the network of thousands of kilometer pipeline is taken to the farm. So just to give you idea, the state is having different river basin. The biggest river basin is the westernly flowing river called Narmada, one of the largest river. And you can see this yellow river basin. And this water, in fact, state got the quota because this river is flowing through 3 states and every state has allocated quota of water. If they don't use, then they lose their rights. So they have to leave the water for irrigation within some time, specified time. So far, government did not do anything, but suddenly they realize if they don't use the water, they will lose their control or their rights on this water. So they have come out with many projects. But the problem is that this river is flowing at a very low elevation and all the command area, all the region is at a higher elevation. So if they have to use this water, they have to put big pumping station to lift the water from river and then take it to the higher elevation. The all command area is situated at a 500, 600 meter from the river basin. So the big size pumping system was required if you have to take this water for irrigation. So just to give you idea, initially I just mentioned they did not do anything with their water. So the cultivatable area was only 0.3 million hectare 20 years back. and now it has reached to 6.5 million hectare. And there are now currently many projects are running, and very soon, within 2 or 3 years, they will reach to 10 million hectare, which is, I think, more than the area of Mexico, irrigated land of Mexico. There are two departments who is driving this project. One is Water Resources Department, state government, and there is this Narmada Valley Development Authority. They form the special purpose vehicle for using the water resources from this river called Narmada. Okay, so you can see, because of this, so many irrigation project, state government has invested. So you can see the progress, the agriculture development. We call it transforming the agriculture through irrigation. The state is growing from 4.5% GDP. Now they are growing at 16.5. This is one of the highest in the country. This state is highest growth area and also driven not by industry, but driven by agriculture. So agriculture growth also, you can see it was merely 0.3. It was negligible in 2003. After 20 years, now it is 19%, very, very impressive. Per capita income is more than 10 times. It was $125 only. Now it has gone to $1,600. Irrigation command area has increased 0.7 million hectare to 4.5 million. And it's very fast growing because of various schemes. And you can see agriculture productivity. They used to take 1,195 kg per hectare was the productivity, which has more than doubled. It is now close to 2,500 kg per hectare. Similarly, you can see there is an impressive growth in the total food grain production and also sugarcane production. So currently, this state has 125 number of large irrigation projects under various stages. By 2025, very soon this year, by end of this year, actually now it is almost close. So estimated command area is going to be 7 million hectare. And I just mentioned they are working very seriously per drop more crop. So every drop of water they want to use to grow more crop. So what they have done one more marvelous job. They have chain of reservoir, various reservoir available. They call it Amrut reservoir, and they have connected this reservoir, and they are also utilizing this water resources very effectively. And there is one big program. This one project, one single project is close to $1 billion and 0.3 million hectare farmland under single project. So this is the size of the project currently are under operation. So I'll quickly take you through. Okay, how these projects are designed. Now I think this is the interesting part, which I think you are looking forward. So every command area under project is divided into chuck. Chuck is the one unit where the size of the chuck is normally 20 hectare. So what they do is they combine the farm of every farmer, make a unit of a 20 hectare, and it is in a local language, we call it a chuck. And this further subdivided into 4 zones, and each zone is like a sub-chuck, which is a 5 hectare. And at a manual on-off wall, they put it at 1 hectare. So 20 hectare divided into 4 zones, 5 hectare, and every 5 hectare divided into 5 1 hectare outlet. And the project is designed in such a way that 20 meter pressure should be available at 1 hectare outlet, which is normally at a farm outlet. And depending on the soil condition and weather condition and the type of crop, we call it a kharif crop. Normally it is a wheat. This area is very, very popular for the high quality of wheat production. So the water, the crop water requirement or the water duty, we call it irrigation duty, is 0.33 liter per second. It varies 0.33 liter per second to 0.35 depending on which zone the project is located in a state. And the complete pipeline is designed in such a way that it delivers 10 times of the irrigation duty. So when we size the diameter of the pipeline, we have to take 10 times the duty. So the irrigation, that is pipeline is designed for 3.5 LPS per hectare. And all this pipeline is underground. And up to 300 mm diameter, we use HDPE pipe. You know this high density polyurethane, which is grade P100. Then 300 mm to 1000 mm, we use ductile iron, which is K9 grade, that is the pressure grade. And above 1000 mm, we use the steel pipe with the epoxy coating, which is a food grade quality. Okay, this is how the distribution network I told you. Suppose this is the river. From river, the water is taken, and this is the complete pipeline, the hydraulic network of the complete command area where we want to take the water. So for every project, government declared the command area, say 10,000 hectare or 20,000 hectare. We are working today on one project whose command area is 100,000 hectares. So you can understand the size of the scheme is such a big. So normally it is divided into many villages, and depending on village, we have the farm record, land record, and from land record is the basis for designing this project. And depending on the topography, the elevation difference, the pipeline is designed using the various hydraulic software like WaterGem or Autodesk. There are many software popular in India. So all those software were used for deciding the routing of the pipeline, the sizing and the diameter, and how do we reach to the every farm that is up to 1 hectare. So it is like a telescopic network of pipeline, the bigger diameter, and as you go away, it goes on reducing, and then we go up to last, it is normally 60 mm. Sometimes it is 3000 meter when you start at the beginning, at the beginning, and the tail end, it goes up to 60 mm or 90 mm, depending on what is the total flow. So any project, if you see, this kind of maps are developed, and we use Google Map for preliminary design of the command area. We call it a command area design or pipe network design. So the Google Map is used. So if the water is too low, I said the water was running at a very low elevation. So first we have to lift the water, pumping station 1, lifting water and putting to pumping station 2, 2 to 3, 3 to 4, like the cascading pumping, series pumping we call it. Once water comes to the height of the command area, and then it goes through the gravity, and then it goes to the different zones. This is how also by schematic. Actually, we have pumping station at the beginning, and then we have pipeline, and on pipeline we have air management system, because this pipeline is underground and we need to have proper venting of the pipeline. So the air release walls are provided, control walls are provided, isolation walls are provided. And at the end, this is at a 20 hectare, which is called outlet management system. Here the control walls are placed. So I'll just take you through quickly to the control wall. This is how the unit, we call it outlet management system, which is installed at 20 hectare. This is like a box. The pipeline is coming, and since it is 20 hectare, 30 hectare, it is 13.5 liter per second. And this is going to every 5 hectare, check. This is the control wall. This control wall is actually operated through hydraulic pressure of the pipeline. And there is solenoid operation, and we use solar energy for operation of solenoid walls. So no pipeline is seen above the ground, everything is underground. So every time the 3 walls are open as per the irrigation calendar or irrigation scheduling, we call it. And then after this cycle is over, another 3 walls will get open, and these are radio connected. So this wall can be operated remotely from a control station or from mobile or from laptop anywhere in the world. So there is a wireless communication system, very advanced. So every wall, every farm can be controlled remotely using the radio link. So this is, it looks like this. The actual picture you can see, this water is coming from the ground, and there's air wall and there's the isolation wall. Here there is again filtration system. So because we want to use the water for sprinkler, it should be clean water. So we filter the water with 200 micron, And here are, you can see the walls, and this is the box in which all the control circuit is mounted. There is a battery. This battery is operated through solar panel. So you don't need any electricity, and the wall also operated through the line pressure. So you don't require any electricity. It is a electricity less and wireless system. And we can control the pressure of the wall by opening the throttling, by controlling the opening and closing of the wall remotely. So this is called a sea wall. And there is a controller and a radio. You can see there is a wireless radio network, which is used for controlling this wall remotely. And there is a web SCADA system, so that in a central control room in the pump house, all these kind of boxes are connected, and you can run the program irrigation schedule depending on what is the crop and what is the season. So complete program can be fed into computer, and it will, the whole system will work automatically. And farmer will get a notification on his mobile if whenever his turn comes, when the water is going to start, 10 minutes before, it gets this SMS on his mobile that your wall water is going to come. So this is how the SCADA screen will look like, where you can see what is the incoming pressure, what is the delta P, what is outlet pressure, then wall open is green, wall close is red. So you know which farm, where it is going, his mobile number, what is the area of a chuck, and then all the position, how much wall is open, how much wall is closed, what is the water going, how much total volume delivered today. Everything is available on a quick click of a button. So this you can access anywhere. You know the temperature, what is there, what is the battery life, what is the sunlight. Everything is monitored remotely. How is the network? So this is a very advanced SCADA system which monitors the every node which is installed at 20 hectare. Okay, this is a central control station which has all the pumping system and SCADA system. So you can operate the number of pumps depending on the water level, the complete irrigation demand in the command area. You can decide how many pumps to be operated. Then there is a VFD, so we can operate higher flow, lower flow. Also, the power is also calculated. So energy efficiency is also taken into consideration. So every pumping station has very advanced instrumentation and control to operate a big pump. These are a very big pump, 3 megawatt, 4 megawatt each pump. So normally each project is 50 to 60 megawatt energy we consume. So we have to be very mindful how we use less energy to pump more water, right? So this is how we do the gateway. There is a radio, wireless radio network, complete command area. We installed like this, the tower. These are the wireless radio tower, which controls all such OMS installed in nearby area. So depending on the topography, the height of the tower and the location of the tower, we decide. And there is a LoRaWAN. These are different technology, you know. Sometimes we use the GPRS, which is a mobile network. Sometimes we use the LoRaWAN, which is another communication radio, wireless radio technology. And all these towers are talking to the remote server, which is on the anywhere in the world. And then it gets connected to the control room. So sitting in control room, you can give command to any outlet to close the wall, open the wall, and what is the demand in the water. If there is a rainfall, we can close all the wall. Okay, this is how I think you are more expert. I will not talk more on the sprinkler irrigation. There are a lot of advantage of sprinkler irrigation because the field is evenly wetted. So uniform plant growth is possible. Okay, this is earlier system of flow irrigation. I think I will not touch because you all are expert. Okay, I'll just take you quickly through one of the project. This is a Nagalwadi project. I think I'll finish in 5 minutes, okay? Here the same Narmada River, this project is lifting 54,000 meter cube per hour. Total pipeline length is 60 kilometers. From here, water is lifted and we are bringing water to here. So this is a 60 kilometer long, total height is 293 meter. The total project is 110 million USD. and 106 villages are getting benefited. Total command area is 47,000, and total power is almost 78 megawatt, and we are consuming 52 megawatt to run the pumps. So this is how the water is coming from a river, and the command area is all at a different elevation. So what we are doing is we are taking water in pumping station 1 to 2, 2 to 3. 3 is feeding water to this command area. Balance water is going to pumping station 4. From 4, there is another command area which is being fed at 10,000 hectare. There is another command area of 5,000 hectare. The balance water goes to pumping station 5. So there is another command area, and similarly, likewise, we are lifting water in 7 pumping station, and along the length, we are going to feed the water to the command area alongside the pipeline. Okay, Willow is my company where I work, is a joint venture involved in this project with one of the large civil construction company who was responsible for construction civil work and laying the pipeline. We did all the automation, we did all the pumping system, we did all the electrical work for this project, and we supplied 36 large pump. Each pump is 3 megawatt. This project is very successful. You can see we supplied 36 pump. Total head is we are lifting water by 819 meter, 15,000 liter per second. There are 7 pumping station. There are 11 rising main, 36 pumps, and total power is 77 megawatt. You can see different pump, and each pump is 3.6 megawatt. Huge machines, huge machines. Okay, these are the just photograph to give you idea. Pumping station 1, which is lifting water from, this is from the delivery side. The river is on other side, back side. So this inside there are pump, and you can see there are 5 pumps, 4 working and 1 standby pump, which is lifting water and then putting it to pumping station 2. These are the big pump. You can see large motor at 3 megawatt inside the pump house. This is another battery of pump in the pumping station 3. This is how the pumping station is looking like, where we are taking. Here you can see only this intermediate pumping station. So you have to manage. This is the only storage of water. So we have to synchronize the operation of pumping station 1 and 2. Otherwise, what will happen? If there is an uneven operation, the flow rate is not balanced, water will spill over, or this pump will not get enough water. So we have to very carefully plan and control the number of pumps so that same water, what is coming pumping station 1, same water goes to pumping station 2 and then 3. This is another very different pumping station. You can see very special semicircular 4-bay. You can see this electrical control system in the same compound. We have similar, the control room here, the control station is installed here, central control station, which controls all the operation of the command area. Here you can see, actually, since the water is taken from river, there are a lot of sand is coming. So what we have done is we have installed online filtration system. The battery of filter, you can see all these are cluster of filters, and all whatever the water is coming from a river through pump is passing through this filter, and they are filtering to 500 microns. So whatever water is going to the command area is filtered water. You can see here the depth of the pump house, because the water level in the river is varying almost 30 meters. So we have to design a pumping station suitable for different water level. After the monsoon, the water is at highest level. And as we go from monsoon to the summer area, the summer season, the water level is depleting and then it goes to low level. So very long pumps are installed inside. And this is also one interesting system, the bladder vessel, because if the pumps are running and suddenly there is electricity failure, all the water which is traveling with high pressures will come back and it will create a big impact, pressure rise, and sometime it may lead to failure of pipeline. So to protect the pipeline from such transient condition, this is called a bladder vessel, which work as a shock absorber. So any shocks because of the transient condition are absorbed in this bladder vessel. So every pump house, this bladder vessel, so this is a highly engineered and very specialized system which protect.
Por ahí, Alberto, si quieres, ya lo tengo para. Nos comentas que hablamos con ellos posteriormente.
Hola, Alberto, ¿nos escuchas?
Una más. Y le mando un mensajito, ¿no? De que vamos a tener una reunión con ellos, todo el seguimiento es una parte bien interesante. Bueno, tenemos nuestro.
Aló, Alberto. Hola, hola. Hola, ¿nos escuchan? Alberto. Hola, Alberto. Coordinador, por favor.
We lost connection, and we are almost out of time. So
Yeah, I am finishing the last slide.
You give us your last 5 minutes. And later, I think we can have another meeting with you and all from the IMTA and the COMEII, our association, to get a better, more information. You can exchange experience what we are doing. So please, and we don't have time for questions. We are out of time. So can you make the conclusion for this, please? Thank you.
Yeah.
Okay.
Yeah. So just to conclude, can you hear me?
Yes, we hear you.
Yeah. So actually, this project was successful because there were a lot of social engineering was done. We involved the farmer in making the project successful. They were explained how the project is going to work, and they were made a stakeholder in the project. So a lot of meeting happened at a village level to explain to the farmer during the construction and after the operation. So there was a social engineering and which led to the farmer empowerment. So the impact of this project is there is a substantial increase in the command area from which was close to 15,000, which led to 47,000. The improved water use efficiency, it actually from say 30%, it led to the close to 80%. So 5,000 hectare area is irrigated with 1 million meter cube of water as against the average of 210. Wheat crop production is increased almost by 3 times. Farmers have started taking not only 1, but 2, but 3 crops in a year. And as I mentioned, there is a good positive social impact, reverse migration from cities to the village. And actually it brought the complete socio-economic upliftment to the region. So I just finished my part. Hello.
Yeah, hello. Can you hear me? Yeah.
Yeah. I finished my presentation.
Yeah. Thank you a lot for participating. I think we need to follow the connection. It was a pleasure. We don't have no time for questions, but we are going to follow with another maybe Teams meeting so we can exchange experience. And what you are doing in India and what we plan to do in Mexico will be very helpful. So thank you, Facundo, Mr. Facundo over there, Vidai, and Professor Ravindra for your talk. I hope we can in the next time we can have more time and we can change more experience. Thank you very well. And nice to meet you, and we thanks a lot. Bye bye.
Thank you so much for giving us an opportunity. What I will do is I will share the presentation to also Dr. Vijay Lapshitwar and also to Facundo. And I request Facundo to be in touch with you so we can work more closely. And I invite, if you are visiting India, please let us know. It will be our pleasure to show you the project site. We can go to the field.
Thank you very much. Thank you, and again. So now we want to send you also our diploma. We prepare a diploma. We send you by a digital form. So thank you. It was signed by our general director for the IMTA for me as president of the COMEII. Thank you. Thank you.
Thank you, my
so
friend
much.
Waldo, for the opportunity.
Gracias. Saludos. Dale. Ok, bueno, vamos a pasar ahora. ¿Quieres pasar? Sí.
Muy buenos días, tengan todas y todos ustedes. Les damos como siempre la más cordial bienvenida a este espacio de conocimiento en línea del Instituto Mexicano de Tecnología del Agua y de la Cátedra UNESCO IMTA, el agua en la sociedad del conocimiento del Instituto Mexicano de Tecnología del Agua.
real placer de estar aquí con vosotros. Es un placer de encontrar de nuevo. Disculpa el español, mi pobre español, pero creo que es importante que voy a hacer la presentación en idioma de español para los amigos del México. Fui en México el 2017 para el Congreso de la ICID. Espero que puede ser que mañana, la próxima vez puede ser que voy a participar al Congreso de ICOL, creo que será en Guadalajara. Entonces espero que puede ser, habemos muchas posibilidades de encontrarse el año próximo. Entonces voy a hablar un poquito en esta ponencia de la... disculpa, ok. ¿Se ve? Sí, ¿puede ver? Ok. Voy a hablar un poquito de los retos de la agricultura de riego ante el cambiamiento climático. Entonces, bienvenidos a la Comisión Internacional de Riego y Drenaje, que está basada en más de 100 países que forman parte de la ICID, cubriendo así más del 95% de la superficie que es regada en el mundo. La oficina central es en Nueva Delhi, como sabes. Es una organización que tiene una historia de 75 años. Se puede decir que ha contribuido de manera determinante para el desarrollo de riego en el mundo, favoreciendo la difusión de los conocimientos, el intercambio de las experiencias y promoviendo la transferencia de las innovaciones tecnológicas en agricultura. Es una organización, una red de profesional que tiene más de, como decía, 100 países que trabaja juntos para mejorar el suministro mundial de alimentos y de la fibra. El objetivo principal es de lograr la seguridad alimentaria y la seguridad del agua también, porque es la garantía de un sustento seguro para una producción agrícola estable. Claro que como organización nos contribuimos significativamente a la consecución de varios objetivos de desarrollo sostenible para la Agenda 2030 con United Nations, con la FAO, IMI, International Water Management Institute, ICARDA, International Center for Agriculture in Dry Areas, and the World Meteorological Organization, IFAD, United Nations International Fund for Agricultural Development. Vamos a comenzar la introducción. Me gusta citar eso essay en 1798 en su famoso ensayo sobre el principio de la población. Thomas Malthus decía que la población, si no es controlada, aumenta en una relación geométrica. Mas la subsistencia, en cambio, aumenta solo en una relación aritmética. Después, la Segunda Guerra Mundial, con la revolución verde, con las grandes innovaciones de proceso y de producto aportadas, permitió un aumento significativo de la producción agrícola, con una tasa de crecimiento medio del 2% anual, proporcionando alimentos suficientes para satisfacer la creciente población de posguerra, refutando las predicciones más pesimistas, ¿no? de Malthus. Entonces, eso es en Italia, ¿no? Eso es la llanura de Catania, es la cosecha. En el 1972, el 12 de marzo, en Roma, se presentó en el Club de Roma un famoso, célebre informe que se llama Los Límites del Desarrollo, Limits to Growth en inglés, fu para la organización de Aurelio Peccei, que era un gran hombre italiano, que dio la idea e encontró, claro, los fondos para que el MIT, el Massachusetts Institute of Technology de Boston, pusiera a trabajar los primeros ordenadores para analizar la compleja red de factores que regula hoy el desarrollo económico, demográfico y material de la humanidad. Es interesante que la conclusión, ¿no?, que de eso ensayo fue que limits to growth are real and not so far in the future. Puede ver que eso es la predicción, ¿no?, de lo que va a pasar hasta el 2100. Entonces, la conclusión principal fue que si la tasa actual de crecimiento de la población, industrialización y contaminación, producción de alimentos y explotación de los recursos continúa sin cambios, los límites del desarrollo en ese planeta se alcanzarán en un momento indeterminado dentro de los próximos 100 años. Y yo creo que estamos muy, muy cerca, ¿no?, de esos límites. Entonces, el gran desafío, ¿no?, para la agricultura, ¿cuál es? Es que en los próximos años la agricultura mundial se enfrentará a un enorme desafío: producir casi el 50% más de alimentos para 2030 y duplicar la producción agrícola para 2050. Es una fecha que nuestro planeta tendrá casi 10.000 millones de habitantes, pero tenemos un 20% menos de tierra cultivable per cápita para producir alimentos. Eso es el gran desafío para la agricultura de hoy. ¿Qué son los factores clave, no? Aumento de la urbanización, uso del suelo. En 1960, un tercio de la población vivía en áreas urbanas, el 60% vivía en las áreas rurales. En 2007, ese reporte estaría 50%. La predicción es que en 2050 un tercio de la población va a vivir en el área rural y 2 de 3 de la población mundial va a vivir en las áreas urbanas. Eso es una slide muy interesante porque va a mostrar cómo en el 1950 la ciudad con más de 5 millones de habitantes era muy pequeña, ¿no? Muy poco. En el 2015 hay mucho más ciudad con más de 5 millones de habitantes.
Recording in progress.
Especialmente en las áreas de la costa, ¿no? Cerca del océano, cerca del mar. Entonces, todos los datos demográficos recientes muestran que las dinámicas de crecimiento de la población han sido particularmente significativas a lo largo de las costas en todo el mundo. Otros factores claves son el cambio de hábitos alimenticios, el aumento creciente de la demanda para usos industriales, energéticos y civiles, el aumento de las superficies agrícolas destinadas a la producción de cultivos energéticos, claro, el impacto del cambio climático en el medio ambiente y la agricultura, y la reducción de la disponibilidad de recursos hídricos, que es un muy grande problema. La ONU, United Nations, dícenos que la escasez de agua afecta a más del 40%, ya a más del 40% de la población mundial. Hay 1.100 millones de personas en todo el mundo que no tienen acceso a agua dulce y unos 2.700 millones que sufren escasez al menos un mes al año para el agua. Hay muchos países de África, Medio Oriente y Asia que tienen graves problemas de disponibilidad de agua y se espera que la escasez de agua aumente más que proporcionalmente para 2040. Aquí puede ver un poquito los países, ¿no?, que son mucho más afectados para la sequía, ¿no? Por eso, las Naciones Unidas hay un target, ¿no? Hay un objetivo que es para 2030 aumentar sustancialmente la eficiencia en el uso del agua en todos los sectores, garantizar la extracción y suministro sostenibles de agua dulce para hacer frente a la escasez de agua y reducir sustancialmente el número de personas que sufren escasez de agua. Eso es objetivo, el target 6.4. Claro, para supervisar los progresos realizados, el indicador SDG 6.4.1 supervisa la evolución de la eficiencia del uso del agua a lo largo del tiempo, medida como la relación entre el valor añadido en dólares y el volumen de agua utilizado. Eso es la evolución, ¿no?, del progress, la evolución de la water use efficiency, de la eficiencia, ¿no?, del uso del agua, segundo el SDG Target 6.4.1. Eso es el año 2000, el 2005, 2010, 2015, 2020. Puede notar, ¿no?, que hay algunos países como Australia, algunos países que tienen muy buena water use efficiency, ¿no? Oceania, América Latina es muy pequeño. Australia, Nueva Zelanda, hay mucha situación muy positiva en términos de eficiencia del uso del agua. Para eso, las Naciones Unidas, en particular la FAO, ¿no?, la Organización para la Food and Agriculture, ha diseñado una iniciativa que se llama Global Framework for Action to Cope with Water Scarcity in Agriculture in the Context of Climate Change. La cifra se llama WASAG. Es una iniciativa, como decía, ¿no?, que diseñada para reunir las principales partes interesadas de todo el mundo, diferentes sectores, para lograr un mejor uso del agua en la agricultura y garantizar la seguridad alimentaria para todos. Tienes muchos objetivos, working groups, como puede ver, ¿no?, aquí en esta slide. Es una asociación que fue iniciada por la FAO, es compuesta de agencias gubernamentales, organizaciones internacionales como LICID, IMI, ICARDA, World Meteorological Organization, universidad, institutos de investigación y asociaciones profesionales. Entonces, la WASAG promueve la colaboración entre sus socios para el desarrollo y la implementación de nuevas políticas, estrategias y programas destinados a optimizar la capacidad de adaptación de las comunidades rurales a la sequía, ¿no?, a la escasez de agua en la agricultura. De nuevo, como decía, puede ver aquí que hay muchos working groups, water and migration, grupos de trabajo, ¿no?, drought preparedness, water and nutrition, sustainable water use, saline agriculture, and maybe some other. Disculpa, en el futuro puede ser que vaya a ser otra working groups, grupo de trabajo. Ahora soy muy feliz de anunciar que el jefe del Technical Advisory Committee de la WASAG, ICID tenía el chair, el presidente, que era el presidente Félix Reinders de la África del Sur. Ahora fue recientemente electo el profesor Chandra Madramutu, que es el dean, es el jefe de la Universidad McGill de Montreal, de Canadá. Entonces, el ICRD, para la segunda vez, tiene el jefe, ¿no?, tiene el chair de Technical Advisory Committee, el comité técnico del WhatsApp. Yo creo que es un señal muy importante para nosotros, para la ICD, para la organización. Ahora, ¿cuál puede ser el futuro, ¿no? Hay un nuevo marco para cartografar las necesidades, el potencial de regadío. Entonces, en ese escenario, la FAO, de nuevo, lanza una nueva iniciativa para mapear las necesidades, el potencial de riego en los distintos países del mundo, definiendo así las indicaciones para la planificación y el desarrollo de riego. Ese programa, el enfoque se llama Irrigation Need and Potential Mapping, IRMA. Entonces introduce un marco que es multicriterio para evaluar y conciliar las necesidades y el potencial de riego en todo el mundo, poniéndolo así al servicio de la seguridad alimentaria sostenible y a largo plazo. El programa se estructura en 4 aspectos principales dentro de un marco multicriterial, idoneidad biofísica, contexto agropedoclimático de la zona, necesidades de desarrollo sostenible, beneficios esperados y contexto socioeconómico y o jurídico institucional. Como puede ver, que este programa hay la World Bank, Islamic Development Bank, FAO, hay IMTA, International Water Management Institute, ICARDA, così via. ¿Por qué es importante? Porque el desarrollo del riego, eso es el gran desafío, ¿no? El desarrollo de nuevos sistemas de riego es una posibilidad muy importante para la seguridad alimentaria, para la seguridad del agua. Entonces, cartografar las zonas más adecuadas puede aumentar la resistencia de la agricultura a los fenómenos climáticos extremos, favoreciendo un uso más eficiente de los recursos hídricos, aumentar la productividad por unidad de terreno y aumentar significativamente la cantidad anual de producción agrícola. Se puede decir que no hay duda que combinado con el uso de las técnicas y métodos más modernos podría permitir de cambiar el paradigma actual de la agricultura a nivel global. ¿Por qué? Porque permite a los agricultores de producir mucho más por hectárea de tierra y por metro cubo, es muy importante, por metro cúbico de agua utilizada. Entonces es muy importante de hacer la transformación del método de riego tradicionales, antiguos, a los más modernos. Eso es el riego moderno, eso es la cuestión, el marco muy importante para hoy. El riego moderno será cada vez más indispensable para mejorar los rendimientos y aumentar la producción de alimentos agrícolas. La seguridad alimentaria de los recursos hídricos debe lograrse necesariamente extendiendo las zonas de regadío e incrementando significativamente la eficiencia del uso del agua. Es por eso que hay un renovado enfoque, ¿no?, en el desarrollo del riego. Eso es la razón para que es muy importante el desarrollo del riego moderno. Sin embargo, su correcta consecución debe basarse en enfoques robustos, basados en una evaluación rigurosa de las necesidades y del potencial. Entonces, tiene que haber mucha información, el suelo, cómo es el suelo, entonces tiene que evaluar, necesidad de evaluar el potencial de riego de cada territorio que vamos a investigar. Entonces, eso requiere la evaluación de su idoneidad pedoclimática, ambiental, las condiciones socioeconómicas de las comunidades, la verificación de la disponibilidad de recursos hídricos adecuados, tanto para el cultivo de los principales cultivos presentes en la zona, como para la introducción de nuevos cultivos. ¿Por qué eso es importante? Porque analizar las necesidades, el potencial de las áreas agrícolas puede guiar a los tomadores de decisiones para planificar las inversiones en el desarrollo de riego, en una escala global, claro. El objetivo final es crear una plataforma común para los investigadores, para los tomadores de decisiones, para mapear el potencial de las áreas agrícolas para el desarrollo del riego y sus necesidades en todo el mundo. Eso es muy importante, todo el mundo. Proporcionando así un sistema de apoyo a la decisión, o como se dice en inglés, Decision Support System, específico para cada país. Aquí puede ver alguna slide. En conclusión, identificar las zonas más adecuadas, evaluar el potencial y sus expectativas de riego, será posible proporcionar a los responsables de la toma de decisiones información adecuada, precisa sobre las inversiones y las necesidades financieras necesarias para los proyectos de desarrollo del riego. Eso es una slide para ver, ¿no?, cómo es la distribución del riego en el mundo. Asia es la más importante área, Américas, África y Europa. ¿Cómo es? Vamos a ver ahora cómo es la situación, ¿no?, de las áreas irrigadas. ¿Cuál es el potencial de desarrollo del riego a nivel mundial? Claro, el potencial para expandir las áreas agrícolas regadas a nivel mundial es relativamente mejor en América Latina, claro, en África subsahariana, como se puede ver. Si vamos a analizar, ¿no?, la superficie adecuada la superficie adecuada para el riego, en amarillo las áreas irrigadas, puede ver que hay mucho más potencial para la América Latina, el Caribe, para el África subsahariana. Contrariamente, el consumo mundial de agua sigue siendo bajo en América Latina, claro, África subsahariana, Asia oriental y sudoriental. Contrariamente, si vamos a observar lo que pasa en el Middle East, en el África del Norte, la región MENA, están en condiciones de sequía, ¿no?, de water scarcity. Vamos a ver el nivel de los estrés hídrico. Es un otro target de las Naciones Unidas, SDG Target 6.4.2. Es un indicador que registra la cantidad de agua dulce extraída de todas las actividades económicas en relación, pero con los recursos totales disponibles de agua dulce renovable. También tiene en cuenta los requisitos medioambientales. Es un indicador un poquito diferente, ¿no?, del indicador 6.4.1 que hemos visto antes. De nuevo, ¿no?, hay la posibilidad de ver en concreto, ¿no?, cómo la evolución del nivel de los estrés hídricos a partir del año 2000, 2005, 2010, 2015, 2020. Es muy fácil de notar, ¿no?, que el nivel de estrés hídrico es muy mejor, va a incrementar, ¿no? Esa es una slide muy interesante, es la extracción de agua dulce para la agricultura, que de alguna manera ensambla, ¿no?, lo que he dicho ahora. Eso es la extracción, va a representar la extracción de agua para el sector agrícola como porcentaje de los recursos hídricos renovables por cada país. Entonces, las extracciones son indicativas de estrés hídrico grave, categoría 4, o críticamente elevado como en categoría 5. Claro, se puede ver de nuevo que la MENA, la región MENA, Middle East, North África, Medio Oriente, África del Norte, es la región con mucho más nivel de estrés hídrico, claro. Eso es interesante porque esa slide, esa mapa, va a describir la porcentaje de personas que son desnutridas por país, medido, claro, para la incidencia en la población total. ¿Qué se puede concluir de esa slide? Importante es destacar que de esa slide que la desnutrición es causada por la falta de acceso a los alimentos, no es por la falta de alimentos disponibles. Esa mapa, de facto, muestra muy bien la importancia del agua para la seguridad alimentaria y también cómo las condiciones nutricionales no siempre están relacionadas con la escasez de agua. Por ejemplo, la región del mundo con la mayor escasez de agua, que es la región MENA, Medio Oriente, África del Norte, está relativamente bien establecida desde el punto de vista nutricional, pero tiene una economía que se basa en la entrada de divisas extranjeras. ¿Por qué? Pero eso dependerá cada vez más de las importaciones para garantir su seguridad alimentaria. Por otro lado, tenemos que recordar que hay muchos países de los trópicos húmedos que tienen un estado nutricional deficiente que pero se puede difícilmente atribuir a la falta de agua, como la África Central, Indonesia, Vietnam. Es evidente que sin las inversiones masivas en infraestructuras de agua y riego realizadas en el pasado, en países como la India, la China, el México o el Egipto, mostraría un panorama mucho más preocupante, que es caracterizado para posibles conflictos internos que son debido a la falta de alimentos. Entonces, vamos a traer algunas conclusiones. El riego moderno es esencial en un contexto de cambio climático. ¿Por qué? Porque puede aumentar la productividad agrícola y puede reducir la pobreza. Pero tiene que ser riego moderno. Es la Smart Agriculture, Smart Irrigation. Entonces, va a considerar que el riego moderno es una buena estrategia de adaptación al cambio climático para las comunidades rurales. ¿Por qué? Puede reducir el impacto de condiciones de mercado imprevisibles y las consecuencias de eventos extremos como la sequía. Y la última, puede estabilizar la producción y los rendimientos de los cultivos. Además, el riego moderno puede permitir de ampliar la elección y, claro, el calendario de los productos agrícolas, con el fin de extender las temporadas de cultivo y también en función de la demanda y del mercado. En un mundo como el mundo actual, que se enfrenta al tema de la seguridad alimentaria, este es un aspecto muy, muy significativo, muy crucial. Dos, hay técnicas y sistemas de riego avanzados que pueden garantizar la seguridad alimentaria. ¿Por qué? Porque se va a accionar adecuadamente. El riego moderno puede reducir las emisiones netas de carbono que son derivadas de las actividades agrícolas. En presencia de un servicio de entrega flexible y puntual en función de una demanda experta, eso es un aspecto muy importante. El uso de las innovaciones tecnológicas más avanzadas permite de conciliar las exigencias de la producción agroalimentaria con un uso sostenible del recurso. Aquí tiene un ejemplo de una experimentación que estamos haciendo en Italia del Norte. Eso es el riego del arrojo con el sistema drip irrigation. Hay resultados que son muy interesantes. Esa es una perspectiva que puede ser muy significativa, muy interesante, porque la sequía, ¿no? la escasez de agua es un problema en todo el mundo ahora. Claro, tiene peor que utilizar sistemas expertos para disfrutar la posibilidad, ¿no? de riego y de la smart agriculture, de la agricultura smart. El tercer aspecto es que la agricultura de regadío puede producir alimentos de forma más estable. ¿Por qué? Porque sabemos, ¿no? Todos nosotros sabemos que los eventos extremos relacionados con el cambio climático pueden alterar significativamente el delicado equilibrio subyacente al ciclo hidrológico del agua. El aumento de las temperaturas conduce a la evaporación, el agotamiento de los recursos hídricos, hace que las comunidades rurales sean muy vulnerables a la sequía. Por lo tanto, la agricultura de regadío moderna puede desempeñar un doble papel, doble objetivo. Para un lado, tiene el potencial de hacer que las comunidades rurales sean mucho más resilientes. Eso es un aspecto muy importante, muy significativo. Por otro lado, las técnicas modernas, como por ejemplo el riego subsuperficial y micropostado de dispensación, lo que se llama ultra low drip irrigation, así como la adopción de sistemas expertos, como decía antes, ¿no? Para la programación de la intervención del regadío, contribuyen en significativa medida a hacer utilizar el agua de manera mucho más inteligente y, lo que es muy importante, reduciendo el desperdicio. Eso es un ejemplo. De nuevo, tenemos mucha experiencia en el norte de Italia con ese sistema de riego que se llama Ultra Low Drip Irrigation. Es una técnica muy innovativa con flow mucho bajo, porque es 0.2, 0.4, 0.2, 0.4 litros para cada hora. Eso es para ejemplar el uso de sistemas expertos. Última consideración, no es muy significativa, no es última para importancia, es considerar el valor económico añadido del riego. Entonces se puede hablar de irrigation ratio, es el informe de riego que va a evaluar el rendimiento técnico-físico de los proyectos de riego en un periodo determinado. Es un parámetro muy importante para el proyecto, ¿no? Para hacer proyectos significativos para el desarrollo de riego. Este indicador representa la relación entre la superficie efectivamente regada y la superficie potencial total y prevista para regar en ese periodo particular. Es un parámetro que yo creo que es muy importante, tienes que tenerlo en consideración cada vez que se hace un proyecto de desarrollo del riego, desarrollo agrícola. ¿Por qué es importante? Porque sobre la base de experiencias que tenemos llevadas a cabo y los resultados de muchos estudios realizados en varias partes del mundo, es posible afirmar que en promedio un aumento del 1% de la relación de riego puede implicar un incremento económico igual, más o menos, a 40-50 millones de dólares US en el valor de la producción agrícola. Solamente el 1% del aumento del irrigation ratio. Entonces va a implementar, ¿no? la condición de las comunidades agrícolas. Eso, claro, depende obviamente de la amplitud de la superficie que va a regar, de la superficie regada, del rendimiento de los cultivos que son utilizados, de las características climáticas y físicas del país o de la zona que está considerada en el marco del proyecto, así como de la particular evolución en cada momento, en cada periodo de los mercados. La eficiencia de riego, irrigation efficiency, otro parámetro muy significativo, muy importante. Entonces, además se puede estimar que para cada aumento del 1%, solamente 1% de la eficiencia de riego apostada para las intervenciones de modernización de riego y o de la innovación tecnológica, se pueden ahorrar en promedio, claro, en promedio hasta 150, 200 millones de metros cúbicos de agua al año. Claro, siempre en función del tamaño de la superficie regada, las propiedades geofísicas y las características edafoclimáticas del territorio que está interesado, que está afectado. Por ejemplo, así puede ver el canal lining, la transformación de canal de riego con riego en presión, la utilización de material moderno como el PVC. Entonces, conclusiones, importancia de riego en la seguridad para conseguir la seguridad alimentaria. El riego ha sido fundamental para garantir la seguridad alimentaria durante los últimos 50 años y claro que seguirá siéndolo en un futuro próximo. Las tierras de regadío representan hoy el 20% de la tierra cultivable del mundo, pero más del 40% de la producción agrícola total proviene del riego. Los recursos hídricos a disposición de la humanidad y actualmente ya comprometidos pueden ser distribuidos de manera mucho más eficiente y racional solo a través del riego. Y por lo tanto, investir en sistemas de riego modernos y sostenibles no solo es necesario para lograr la seguridad alimentaria, sino que también es esencial para garantizar un equilibrio ambiental adecuado y preservar los recursos hídricos de la humanidad. Muchas gracias por vuestra atención. Eso es mis datos de contacto. Muchas gracias.
Gracias, doctor Marco Arcieri, por esta interesante charla. Qué inmejorable forma de comenzar con estos trabajos del Décimo Congreso Nacional y Tercer Congreso Internacional de Riego, Drenaje y Biosistemas. Qué mejor forma que con el marco que nos presenta usted en esta ocasión, en la apertura de este importante congreso en México, y que se haya conectado con nosotros desde allá para hablarnos de los retos de la agricultura de riego ante el cambio climático. El doctor Marco Arcieri, presidente de la ICID y del Comité Nacional de la ICID en Italia. Nosotros muy agradecidos en nombre de todos los presentes aquí en la sala de congresos del Instituto Mexicano de Tecnología del Agua en el estado de Morelos, y también a quienes nos acompañan a través de las redes sociales, tanto del Instituto Mexicano de Tecnología del Agua como del Colegio Mexicano de Ingenieros en Irrigación. Todos muy agradecidos de poder tener la oportunidad de escucharle en esta ocasión. De momento no tenemos mucho espacio para hacer un intercambio con los presentes, pero sí queremos tener la oportunidad de saludarle pues próximamente en el Congreso de Grandes Presas que se realizará en nuestro país, en la ciudad de Guadalajara, doctor.
Sí, claro. Será un grande placer para mí de volver en México, porque el México es un país increíble, es historia, tradición, es un país latino, ¿no? Entonces, se puede decir, ¿no?, que es un país latino. Entonces, será muy contento de volver a ese magnífico país, de descubrir otra área del México, porque última vez fui en Yucatán, en Ciudad del México, Yucatán. Entonces, próxima vez voy a Guadalajara, que es un poquito diferente, ¿no? Entonces hay la posibilidad de descubrir otra área de ese magnífico país.
Correcto, y la gente siempre muy hospitalaria y muy
Sí.
de recibirle y, por supuesto, de agradecerle su presencia en esta inauguración del 10º Congreso Nacional y Tercer Congreso Internacional de Riego, Drenaje y Biosistemas. Pues brindamos un fuerte aplauso que estamos en la sala para el doctor Alfieri, por favor.
Muchas gracias, muchas gracias. Ha sido un bello placer para mí, bello placer. Un honor. Thank you.
El gusto es nuestro, y recordar a todos los que nos acompañan en redes sociales que si no tuvieron oportunidad de presenciar las conferencias magistrales íntegras o si saben de alguien que hubiera estado interesado en presenciarlas y no tuvo la oportunidad de conectarse en vivo, pues lo podrán hacer en cualquier momento, tanto en las redes sociales del Instituto Mexicano de Tecnología del Agua como en las redes sociales del Colegio Mexicano de Ingenieros en Irrigación. Muchísimas gracias, doctor Marco Arciero. Lo esperamos por México próximamente.
Muchas gracias, muchas gracias.
Gracias. Hasta pronto. Y pues dando continuidad al programa que tenemos para la primera de las 3 jornadas de este Congreso, vamos a dar paso a la tercera conferencia magistral que tendremos este día. Es la última de las conferencias magistrales que tendremos en esta jornada. Y esta
a este seminario en línea de la Cátedra UNESCO.
Departamento de Rendimiento y Cultivo de la universidad, sobre todo universidad en Italia, tiene un doctorado también en la Universidad de Basilicata, ¿sí? Y es miembro del ICIT y ha ocupado diferentes cargos, fue vicepresidente, de hecho lo conocí cuando era vicepresidente, fue representante también, y es el representante del ICIT entre organismos con la ONU, la FAO, ¿no? Entonces, tiene toda una experiencia, sobre todo en la parte de gestión del agua. Bueno, vamos a pasar ahora a su presentación. Doctor, es un gusto nuevamente. Vamos a compartir.